Hello, and welcome back to this series where I teach you how to do archival data research using Matlab. So we're going to start a completely new topic in this video, and I've already started the code that we're going to do here. We're going to show you how to compute abnormal stock returns, daily abnormal stock returns, using the Fama-French 3-factor plus the Carhart momentum factor model. So the 4-factor model, often just referred to as the Fama-French 4-factor model. Only 3 of the factors are really we should give Fama and French credit for, but the 4th factor, momentum, this Professor Mark Carhart is the one who came up with this idea, published the paper that established that there's this momentum factor that can explain stock returns. So the first thing we need to do, obviously type our commands that we always type at the beginning of every code. Clear workspace and clear the command window. And then we're going to bring in the data. And this is firm level data that I've already downloaded from CRISP. And I actually need to point my folder back to our folder here, which also has the same data set in it. So it's this data set. It's daily rates of return for all stocks in the CRISP universe over the time period 2019 January through 2023 December. So a 5-year calendar time period. So let's see what the data looks like here. It's a big data set. So it takes a little bit of time to load. Takes a lot of time to load, it looks like. So I'm just reading this data in as a table. We're going to look at the variables that are in the data set. So you can see it's 10,793,523 rows. So a rather big data set. We have the perm node, which you should know. That's the security identifier in CRISP. That's how the CRISP data identifies a security uniquely as the perm node. Then we have the day, in this case January 2nd, 2019 for this particular security. Here's the share code. We've talked in previous video that we only want to look at share codes 10 and 11 because those are the common stocks of companies. Here's the 4-digit SIC code, and here's the daily return for that security on this day, which includes any dividends and is adjusted for stock splits. All right, so this is daily firm return data. It's the CRISP universe over the sample time period January of 2019 through December of 2023, like I said earlier. And what I'm going to show you in this video is how to compute the abnormal return for a given day, for a given security. This is the actual return. How do you compute the unexpected return? And so that's just going to be the expected return, or the actual return minus the expected return. That's the abnormal, or the return that we would not expect. So it's this number minus the expected return. And what is the expected return? Well, that's where we got to do a deep dive. I'm going to have to teach you a few things. So there were two professors in finance, Eugene Fama and Kenneth French, who in the early 1990s, they published a couple of papers in the top finance journals in which they showed that it's their three-factor model. They showed that there are three portfolios, and returns on those portfolios can explain the returns on any other portfolio or individual stocks, can explain the majority of the variation in returns on other portfolios or other stocks. In other words, they basically modeled returns. They developed a model for expected returns. That's the thing. We need some model that would give us an expectation for what we would expect returns to be. I mean, a simple expectations model would be, so for this security, for this date, what would we expect the return to be? Well, we could say maybe we expect it to be the average of the previous 30 trading days of returns, or the average of the previous 90 trading days of returns, and use that mean as what we would expect the return to be on this trading day, and then take that expected return and subtract it from this actual return to get the abnormal return. That's one model of expected returns. But that model was shown by many researchers before Fama and French to not be a very good model. That was not a good model of expected returns. What Fama and French showed is that their three-factor model performed really well. In other words, when you regress the returns of any portfolio of stocks or individual stocks, if your portfolio only has one stock, if you regress the returns of, let's just say, take one stock, if we regress its returns on the returns on these three factor portfolios, then the R squared of the regression is about 0.85 or 0.88. In other words, 85 to 88 to 90% of the variation in the returns on your stock can be explained by variation in these three factor portfolio returns. That's a pretty darn good model of expected returns. Later, a couple years after that, so that was in 1993. So in 1997, Mark Carhart, he published a paper where he showed that there's an additional factor that can actually help to explain returns. And he showed that if you include the return on the momentum factor portfolio with the Fama-French three factors, then the R squared of the regression gets even higher, up in the 90%. And so since then, researchers usually in finance and accounting, they use this four-factor model as the model for expected returns. And so where do we get the returns on those four different portfolios? Where's that data? That data is publicly available. You just go to Ken French's website. If you come in here, I'll make it bigger so you can see it. If you come down here, Fama French three factors, we download this CSV file. I'm going to put this in our whoops, I'm in the wrong place. I'm going to put this in our data folder. Actually, you know what? Let's go ahead and put this in our downloads folder. So I'm just going to download it and put it in the downloads folder. It's a zip file. And then I'm going to come over here and get the momentum. And that's the daily. Those are the daily factors. I'm also going to get, well, we'll leave it at that for that. And then I'm going to come down here and try to find the momentum factor data right here, the daily momentum factor. Put that in our downloads folder. All right, so that's the data that we want. What I want to do is I'm going to take this out and put this in our folder, and then I'm also going to put both of these files in our data folder here. I'm going to rename this. I'm just going to call it, let's see, I'll just call it Fama French Factors. Actually, I want this to be an Excel file because I'm going to put this data with this data, put it all together. So let's open this. Let's go ahead and save this as an Excel file. And we can save it in the same place with the same name. Hit save. And then on this sheet, I'm going to rename this. I'm just going to call this the 3 factors daily. And then on this sheet, and you know what? I'm going to go ahead and get rid of this. Give this variable the name day. I'm going to change the names of all these variables to lowercase. And I'll explain these variables here in a second. Save that. Then this sheet we're going to name momentum factor daily. And then that other file, where is it? This file here. I guess I can just open this and copy and paste the data into here, starting right here. Put that there. Call this day and then call this mom for the momentum factor and save. Control S. Then I can close this, and then we don't need these 2 CSV files anymore. We have our data right here at the Fama French factors. All right, then I'm going to close this, and then we're going to bring in those data sets. I'm going to call the 3-factor data set market 3-fact data. So I'm bringing in this data, but which sheet do I want to bring in? When you bring in a CSV file, it only has 1 sheet by default, so you don't have to specify. But with an Excel file, you have to specify. So sheet, the sheet that has the name 3 factors daily. Preserve variable names, set equal to true. So this brings in the market. This loads the market. Fama French 3 factors. Up here we loaded the daily firm returns. And then this next file I'm going to call the market momentum data. Keep in mind, these 2 data sets are publicly available. I showed you where to get them. Obviously, this data set here, you have to have a subscription to CRISP to be able to download that data, which I've already downloaded it. Oh, whoops, I chose the wrong file here. Come on. By default, it should list all the files that are there. There we go. And which sheet do we want here? We want the momentum factor daily sheet. So this loads the market Carhart momentum factor data, named after Professor Mark Carhart. All right, let's go ahead and load these data sets. They're a lot smaller than the other ones, so they should load pretty much instantly. Oh, I misspelled right here. There is an preserve variable names. So I loaded, it ran that line, but it didn't run line 17. So all right, so here we go. So here's our market 3-factor data. And it goes all the way back. Ken French has the data all the way back 1926, beginning on July 1st. And then every single trading day from 1926, July 1st, all the way through, it looks like April 30th of 2024. He updates the data once per month on his website. So we have pretty much current data for every trading day over this time period. We're going to have to get rid of these two NaN rows, but that's easy to do. And so in this column, we have the return on, and this is these are percentage returns here, not rates of return. So we need to divide these by 100 to get the rate of return. They're already converted to percentages. So this number right here is the percentage rate of return on the whole market of stocks for that trading day that existed at that time. If you held the whole market on that trading day, you would have earned a 0.1% rate of return, minus the risk-free rate. So this is the excess rate of return. So this is what you would have earned on the market portfolio minus this. This is the risk-free rate as of that date. And the risk-free rate is taken from the U.S. Treasury Department. It's basically the rate you would earn. It's the 1-month Treasury bill rate, but converted back to a daily rate, because this is for one day here. And this data is publicly available. So Ken French has gathered that already and put that here. Then he's computed the market rate of return you could have earned on this trading date, and then subtracted that, taken that market rate of return and subtracted the risk-free rate to give this. So if we want to get the actual market rate of return, we have to take this and add back the risk-free rate, which is what we're going to do. So the market rate of return, the rate of return on the market portfolio is one of the factors. SMB, this is the rate of return on a portfolio where you go long. You buy small stocks, and by small, they have a specific definition in their paper, if I'm in French. I'm not going to go into all the details, but you buy a small portfolio, a portfolio of small stocks, smaller companies, and you also, at the same time, you go short or you sell short large companies, and that's your portfolio strategy. And so the small minus big portfolio return for this date was negative 0.25%, for example. And then the HML factor, this is a portfolio where you go long in high growth stocks, high H, and you go short low growth stocks or high value stocks. So the SMB stands for small minus big, and the HML stands for high minus low. And these are the rates of return, respectively, on these two factor portfolios. This is the rate of return. If we take this and add back the risk-free rate, then we have the rate of return on the market portfolio. And so the rate of return on the market portfolio, the rate of return on a portfolio that goes long small stocks, minus the rate of return that goes short big stocks, and then the rate of return on the portfolio that longs the highest growth stocks and shorts the low growth stocks. The rates of return on those three respective portfolios, Falma and French found in 1993 that those rates of return explain, 85 to 88% of the rates of return of any portfolio. And so that became the de facto model for expected returns. In other words, you can expect a given portfolio you own or a given stock you own, you can expect what the rate of return you will get will be, and it'll be related to the rates of return that you would get on these three portfolios. And then Carhart's in 1997 found that there's this other portfolio, momentum portfolio, where in the momentum portfolio is where you long stocks who in the previous certain number of trading days performed really well relative to other stocks in the market. And then you short stocks, you sell short those stocks who in the previous trading days performed very poorly. And so the rate of return on this momentum portfolio also is really good at explaining the returns on other portfolios. When you put this in, the 4 factors, the market return, SMB, HML, and the return on the momentum portfolio, the returns on these 4 portfolios can explain 90 to 93% of the returns on any portfolio. And so this 4-factor model became known as the just a Fama French 4-factor model, and it became the de facto for finance and accounting researchers when you're estimating return, when you're computing expected returns. You need a model, and that's the model that we use. Now this data only it goes back 1926, but starting in November 3rd, and goes all the way every trading day, all the way until April 30th. So this data pretty much covers the exact same time period as this data, but not quite, because there's this time period between July 1st and November 3rd where this data has observations, but the momentum data doesn't. But none of that really matters, because all we care about with our firm data is from January of 2019 through December of 2023. And so all that data is way down here, so we're fine. So let's go in and delete all the rows with at least one NaN value in our market three-factor data and our other market momentum data. So you should remember this. You should remember this code that I've typed before to delete any row that has a NaN value in at least one of the columns. So we'll do that. And then the same thing for all right. And then what we're going to do is we're going to join these two together. We want the 4 factors to all be in the same data set. We're going to use day as the joining variable because they both have that variable. And we're going to rename a table. We're going to call this table, not rename, but we're going to create a new table called 4 factors data. And it's going to be the inner join or the merging of market 3-fact data with market momentum data. And on which variables are we going to do the merge? On the day variable. And then we can go ahead and clear these 2 data sets because we don't need them anymore. Because after we join them together, we don't need them anymore. So now in our 4 factors data, it's going to start on November 3rd because the momentum data started on November 3rd. The other data set started on July 1st, 1926, but momentum started on November 3rd. So when you join together on day, and we have our this is the excess market rate of return. the market rate of return minus the risk-free rate. We need to add that back to the risk-free rate. We have SMB HML and the momentum. So now we can also up here do the same thing with firm data. Actually, I don't know if it will work because our date variable is date time, whereas over here our date variable was double. Right. So in these two data sets, our date variable was a double, and therefore we could do this way to delete rows with at least one NaN value. But since in our firm data table, the date variable is not double, it's date time, we can't apply the same code. I don't think we can. So if we try, like in other words, if we try to do the same thing that we're doing here, because we also need to delete from the firm data matrix any row which has a NaN value in any column. So we'll see if this works. If I recall, this won't work. No, it has to do with the date time thing. So, and if we try to do it this way, I don't believe that works either. Yeah. IsNaN, you can only use IsNaN with a double, not with a table array. And so we have to have those curly braces, but then date time and double don't align. So that's why this won't work. So that's fine. What we're going to do next is we're going to create a double array from our firm data table, and we're going to convert the date variable to double data type from a date time data type. So we're going to let A, I'm just going to call it A, equal our firm data, all rows, column 1, the double portion, that's why we have the curly braces. All rows, column 1, that's a double already. These other ones are all double except for date, which is a date time. And so then in column 2 of A, we're going to use the YYYMMDD function applied to column 2 of firm data. All rows, column 2, the double, the non-tabular portion. And the YYYMMDD converts this column from a date time to a double. And then for columns 3 through the rest of A, that's just going to be columns 3 through the rest of all rows, columns 3 through the rest of firm data. So we'll do that. Oh, I misspelled this, sorry. I misspelled this here. So we'll do that. And here's A now. Now we have our day looking like this and it's a double data type. Then we'll delete any we will remove all rows where the share code is neither 10 nor 11. These are the common stocks of firms. We only want to keep those rows. So the share code's in column 3. We only want to keep those observations where the share code is 10 or 11. So if the share code is neither 10, not equal to 10, and it's not equal to 11, if it's neither of those, or neither of those, however you want to pronounce it, So those rows, all columns of A should be deleted. So A gets a lot smaller, as you can see. And then we will delete any row of A where there is a NaN value in any of the columns. We'll do that because we haven't done that yet. So A goes to 4,982,120 rows. And it started at 10 million something. We removed a lot of those observations, more than half, mainly because they had share codes that weren't 10 or 11. Those securities, we don't want them in our analysis. Now we can remove the share code variable itself because we don't need that variable anymore. Because we know we're left with only share codes 10 and 11, so we can go ahead and remove column 3 from A. So we'll say all rows column 3 of A, delete. Let's do that. Now we will create a double array for the factors data, and we will remove the risk-free rate. So here's our factors data. We're going to create a double array. These are all double variable data types, so we can create a double array very quickly by we're going to call it B. So B equals 4 factors data, all rows, columns 1 through 4, and then column 6. We're not keeping the risk-free rate. Actually, you know what? We're not going to keep the risk-free rate. This is the factor that Fama and French actually have determined. So it's the excess market return, the rate of return on the market portfolio minus the risk-free rate of return. That's the first factor. Then SMB, then HML. We don't have to add the risk-free rate back to the market return. We're going to keep this by itself. It's the excess rate of return. So the 4 factors are the excess rate of return on the market portfolio, the rate of return on the SMB portfolio, small minus big, the rate of return on the HML portfolio, and the rate of return on the momentum portfolio. So we just need to keep columns 1 through 4 and then column 6. So now B is a double array. This is our 4 factors data, our factored data, and this A obviously is our daily firm returns data set, our firm level data. All right, and then we're going to remove all dates from the market factors data that are less than the earliest and greater than the latest data in the firm data. Dates, the firm data. In other words, our firm data goes from January of 2019 through December of 2023. And so any data in our factors data set here that is before January of 2019 or after December of 2023, we don't need that anyway. And so all we have to do is say B. Which rows of B do we want to be eliminated? Well, we want to find those rows where in column 1 of B, which is the day column, where it's less than the minimum of the day column in the firm level data, which is in matrix A. In other words, all rows of B where in this column a number is less a date is less than the minimum of the dates in this column. The minimum is this date right here. So all of those rows of B, or vertical sign for or when you're doing a logical operation in Matlab, or all those rows in B where the date is greater than the maximum of what you would find date-wise in A. So all these rows of B all these rows of B, I have forgotten to put a, see, I'm sure you know what the min and the max functions do. So all these rows of B, all columns we want to delete. So you can see B is going to shrink from 25,631 rows all the way down to 1,258 rows. You can see in B, the first date we have is January 2nd, 2019. And the last date we have is December 29th, 2023. That must have been the last trading day in calendar year 2023. December 30th and December 31st weren't trading days. A trading day is a weekday. It's not a weekend. It's usually a weekday, unless it's a holiday, and then obviously it's not a trading day. On average, there's about 250 to 252 trading days in a given calendar year. These are days where the stock exchanges are open for business and trading occurs. All right. And now what we want to do is I want to explain theoretically what we're going to do next. I guess before we do that, I can go ahead and do a couple more things. What we're going to do is we're going to set our estimation window. I'm going to let W be the estimation window parameter. And I'm going to set that equal to 90. So this is the number of trading days in our estimation window. 90 is the minimum, and 120 is the most common by researchers. So your estimation window should be bigger than or equal to 90, and 120 is most commonly used by researchers. The bigger the estimation window, the fewer firm days for which abnormal returns or unexpected returns can be computed. So that's something to keep in mind. I'll keep that in the comments. Then we want to make sure that our matrix, that our firm level data is sorted by firm and then by day. So we're going to sort the rows of A by column 1 and then by column 2. Column 1 is the perm number column, the firm column, and column 2 is the day column. Now it's already sorted by firm and then by day. If you can see here, it's already sorted in ascending order by firm and then by day. So because CRISP does that automatically, but I go ahead and run this line of code. Run both of these because we haven't run these yet. You want to get in the habit of doing that. I should have put a semicolon here. I didn't. That's why the output showed up right there. Want to get in the habit of sorting firm level data by firm and then by day. Even though it's already done for us, make sure. And then we're going to let U equal the unique firms. So it'd be the unique values in the first column of A, all the unique perm nodes. And the reason we're going to do that is because we want to make a little matrix for each firm's data. So for example, this security 10026, we want all of its data in its own little matrix, and so forth and so on. So we'll do a for loop. I've done this before in previous videos. We'll let I go start at 1, increment by 1, and go up to however big U is in the row's direction. So U, there are 5,331 unique firms over this 5-year sample time period for which trading data that we had in CRISP. So we're going to let I go start at 1, increment by 1, and go up to however big U is in the rows direction. This means rows direction. This means columns direction. And U in the rows direction is 5,331. There's 5,331 firms. And we're going to let firms 1, comma I, row 1, column I. This is a cell array because of the curly brace. So each cell in the array is itself a matrix. So those rows in A, where the firm equals that particular firm in U. So this creates a cell array of unique firms where each firm has its own double array matrix of data in the for loop. So in the first little matrix, firms 1, comma 1, we're going to get that portion of A, these rows, all columns, that portion of A where U11 equals those perm numbers in column 1 of A. Column 1 of A is the perm no column, this column. And we're finding all those rows in A where in column 1 it equals 10026. So it turns out it'll be the first 1,258 rows, I believe. All columns, that'll be its own little matrix. So this may take a second. But we'll let it run here. The next part of our code, while it's running, I can tell you, the next part of our code, it will be the hardest part. And it will take a little while to run. So I'll definitely have to I'll have to stop the video but I'll splice everything together so it looks like it was seamless. But it usually takes, not this part, but the next part we're going to do usually takes like 30 to 40 minutes to run on a fast computer. But it's the meat of the code. It's the heart of what we're doing. So here's our firms matrix. Now our firms little cell array has, each one is its own little matrix, right? So here's all the data for that first firm. Here's all the data for the second firm, 10028, the second firm in our U right here. All the data for that third firm, 10032, should be in the third matrix right here, and so forth and so on. Let me close the variables before they get too many in the RAM memory. I mean, they're still in RAM memory, but I'm going to close them and open it back up. Let's just look at this first firm. So what we want to do, now I want to talk about the theory behind this. What we want to do is we want to compute the abnormal return for a given firm on a given day. That's what we want to do. And so there's a several step process to doing that. And unless we get this in our heads exactly what those steps are, unless we get this in our head, it's going to be hard to actually think about how to write the code to make it come about. So we're going to model this here on paper. So what we're going to do is I should make a set of steps here. So step 1, for computing abnormal returns. Or unexpected returns, if you want to call them that. Step 1, we're going to use the previous W. In this case, we set W equal to 90. We're going to use the previous W daily returns to estimate equation 1. And here's our equation 1. R is the actual rate of return for firm I on day T. And we're modeling that as a linear combination. We're modeling that as a linear combination. So we have a coefficient beta 0, a constant beta 0, plus a constant beta 1 times something, plus a constant beta 2 times something, plus a constant beta 3 times something, plus a constant beta 4 times something, plus an error term, epsilon, for firm I, day T. We're modeling the return, the actual return, for a given firm on a given day. We're modeling it as a linear combination of the returns on those 4 factor portfolios. Return on the market portfolio on day T, the return on the small minus big portfolio on day T, the return on the high minus low, high growth minus low growth portfolio on day T, and the return on the momentum portfolio on day T. So this is our expectations model. It's a linear expectations model. And so we're going to run this regression. We're going to regress the previous W daily returns these guys. We're going to regress the previous W daily returns to estimate this equation. We're regressing the daily returns for firm I, day T, over the previous 90 days. So that's 90 different numbers, and we're regressing that on the market rate of return, or this should be the market excess rate of return. This is the market minus the risk-free rate here, but I'm just going to call it the market. The rate of return on the SMB portfolio, the rate of return on the HML portfolio, and the rate of return on the momentum portfolio, plus an error term. So in step 2, let's finish step 1. So step 1 will produce, when we run that regression, what happens? It will produce a beta 0 hat, which is an estimate of the true population parameter beta 0. It'll produce an estimate of beta 1, an estimate of beta 2, an estimate of beta 3, and an estimate of beta 4. So these 5 estimates are what we want to keep. Then we move to step 2. So we model expected returns, or I should say, we compute our expected return as follows. We compute the expected return. So our expected return, I'm going to call it ER, expected return for firm I on day W plus T, where T starts at 1 and goes all the way up to however big our sample size is in terms of number of days of observations. So our expected return, so we run equation 1, let W equal 90. We run equation 1 over the previous 90 trading days. That gives us estimates, these 5 numbers. And then the expected return for that firm on day 91, W is 90, plus big T, if T equals 1 on day 91, would be equal to our estimated intercept plus our estimated beta 1 times whatever the actual market rate of return was on that day, 91, if T, big T equals 1, plus our estimated beta 2 coefficient times whatever the actual rate of return on the SMB portfolio was on that day, plus our estimated beta 3 coefficient times the actual rate of return on the HML portfolio on that day, plus our beta 4 coefficient times the actual rate of return on the momentum portfolio on that day. Move this over a little bit so I can have room to write. That's our expected rate of return for firm I, day W plus T. Now, another way to write this is we can write this using matrix algebra. We can take our vector of estimated coefficients, beta 0 hat, beta 1 hat, beta 2 hat, beta 3 hat, and beta 4 hat. Now that is a 1 row by 5 column vector. And we can multiply that. Let me give myself room here. So what I'm writing now is just the equivalent of this, but I'm doing it in matrix algebra form because after all we are using Matrix Laboratory. We're going to do this in Matlab. Multiply that by a column vector, a 5 by 1 column vector. So we're allowed to do this matrix multiplication because the number of columns of the first matrix equals the number of rows of the second matrix, so we can multiply those two together. We're going to have a 1. We're going to have the market rate of return in day W plus T here. The SMB rate of return, day W plus T here. the HML rate of return, day W plus T here, and the momentum, the rate of return on the momentum portfolio in day W plus T here. And you can see what is the product of these two matrices, or these two vectors, if you will. You got beta 0 hat times 1, that's this, plus beta 1 hat times the market rate of return in W plus T, that's this, and so forth. So that's another way to write it. And notice when we take a 1 by 5 vector multiplied by a 5 by 1 vector, our result that we get is a 1 by 1, it's just a number. And that number is our expected rate of return for firm I on day W plus T. So finally, step 3, our abnormal rate of return for firm I, day W plus T, is equal to our actual rate of return for firm I on day W plus T minus our expected rate of return for firm I, day W plus T. This was calculated here. This we already know. That's given to us. And there we go. We have our abnormal rate of return. We'll call this equation 2. So it's these three steps that we have to do in Matlab. To run equation 1's regression, you need all of the previous W daily returns. If there's any missing daily returns on your firm, you can't run this regression. There won't be any missing observations on the market factor returns. That's a complete data set. There won't be any missing observations on the market, on the market factor, the SMB factor, HML, momentum factor. That's a complete data set from Ken French's website. It has no missing trading days. So if there's missing observations on our particular firm's daily data, in other words, unless we have all 90 trading days, we can't run this regression and therefore can't compute the expected rate of return in day 91 and the abnormal rate of return in day 91. You see what I mean? So that's why what we said earlier about the estimation window, most researchers use 120 returns. So they run the regression with 120 observations in it each time. And that's a more stringent requirement than only 90 days. So you can see if you require the firm to have 120 consecutive trading days of observations to be able to run this regression equation 1, then we're going to even have less firm days for which we can compute the abnormal returns, because there'll be so many missing observations that we can't even compute things. So that's how to theoretically compute the abnormal return for a given firm I on a given day. So now what we want to do is we want to do that in Matlab. So we just need to think. So I'm going to go ahead and the next block of code is going to compute the abnormal rate of return for each firm day for which we have non-missing rates of return for each day in the previous W day estimation window. The abnormal rates of return, or the abnormal rate of return for a given day is the actual rate of return minus the expected rate of return, where we use the Fama-French 3-factor plus momentum factor model to compute expected rates of return. Compute the expected rate of return using that regression approach. All right. So if we look at our firm's cell array here, each firm has its own matrix. So if the size of a given firm's matrix is not at least 91 days, we can't even compute any abnormal returns for any days for that firm, right? The firm has to have at least 91 observations. The first 90 we will use to run the regression and get the estimated coefficients. And then we can compute the abnormal daily return on day 91. But if it doesn't have at least 91 days, say it only has 90, we can run the regression to get the estimated coefficients using those 90 days. But then to compute the abnormal daily return on day 91, well, they don't have day 91. So they got to have at least 91 daily rates of return to even be able to compute abnormal rates of return for them. So what I'm going to do is I'm going to basically look through my firm's cell array and look at the number of rows in each one of these matrices. And if there's a given matrix which does not have at least 91 rows, I'm gonna delete it. For example, there will be plenty of examples. It's hard to find them by eye, but so let I start at 1, increment by 1, and go up to how many ever columns there are in the firm's matrix, in the firm's cell array, which there are 5,331. That's the number of firms. We'll do it this way. And we'll say if, it's an if-then statement, if the size of that particular firm's matrix in the rows direction is less than W plus 1, then we want to set that firm's matrix to empty. In the if statement in the for loop. And so you'll see there'll be plenty of firm matrices that are empty. Like if we just look through here, let's see if we can spot one. I spotted one. There's one. That firm must not have had at least 91 trading days. And there'll be plenty of them. So there were 5,331 firms. Now what we want to do is delete any firm's matrix that's empty. By using this, we'll say firms equals, you can just copy and paste this code. I'm not going to try to explain it. So there's this cell function. We're finding all places in that cell array where a given matrix is empty, and we're deleting it. So firms by itself is a cell array, and we're deleting any particular entry in firms. And each entry is itself a double array matrix. We're deleting any entry which is empty. So you'll see that firms, it was 5,331 columns. Now it's 5,194. So it didn't delete a lot, but there were several firms. There were, about 150 firms that didn't have at least 91 trading days of data. All right, so now we're ready for the hardest part of this program. But right before we do that, let's look and make sure. So if we look at our market factors data, we can see we still have that as a percentage rate of return. But in our firm's data, we have it as a rate of return. So we need to convert the market factor data to just a rate of return. So we'll set B, all rows column 1, that can stay the same. But then columns 2 through end, we want to divide that by 100. So this converts the market factor percentage returns to rates of return. We need to do that first before we do this next step. So in the firm's matrices, we have rates of return, and in our market factors data, we have rates of return. Now the next part of this code, it takes a while to run. So what I'm going to do is I'm going to enclose it within a tick-tock. Whatever code is enclosed inside of a tick-tock in Matlab, when it runs this block, including what's between here, as soon as it runs the tick, it starts a timestamp, and then as soon as it finishes this code that's inside of here and runs the tock, it also records a timestamp, and then it subtracts this timestamp from this timestamp, and it spits out the difference in seconds on the screen after the code is run. So you know exactly how long it took for all this code in between here to run. And the block that we're going to type takes about 30 to 40 minutes on a fast computer. So it's useful if you think that your code's going to take a while to run. Enclose your code within a tick and a tock, then you'll know how long it takes to run, so that if you run it again at some point in the future, it takes, say it takes an hour and a half, you have an hour and a half where you can leave your computer and go do other things, just come back 90 minutes later and it'll be ready to go. All right. So now what we want to do is we want to, within each firm's matrix, what we want to do, just like we had shown you theoretically on paper here earlier, is we want to run those regressions. So for this firm, for example, we want to make sure that these first 90 returns, or W, we have W set equal to 90 here, that these first 90 trading days of returns here, we want to make sure that they're consecutive trading days. We want to make sure there's no gaps. And if there are no gaps, then we want to regress these 90 returns right here. This is our dependent variable. Regress those 90 returns on our independent variables, like we showed you theoretically. Equation 1 earlier. We want to run that regression. This is the market rate of return, excess market rate of return. This is the SMB rate of return, HML, momentum rate of return, factor rate of return. These are the portfolio rates of return on those 4 portfolios respectively. That's our independent variable. Those are our independent variables. We want to regress this dependent variable on these 4 independent variables. Now we know these trading days here have no gaps. The market data has no gaps from Ken French's website. So these are consecutive trading days. There are no missed trading days here. But in our firm's matrix, these dates here may have gaps. We just need to ensure that they don't have any gaps. For example, if, let's say for this particular firm, we were missing the January 3rd, 2019 return. In other words, this row is missing. Then all these other rows would move up, right? And on the second row here, we would have January 4th, 2019. And then on the third row, we'd have January 7th, 2019. So then if we regress those first 90 returns on these 90 returns, there would be the first observation on the dependent variable would be this number for January 2nd. That's correct. The second observation on the dependent variable would be this number for January 4th. And the second observation on the independent variables would be those observations that relate to January 3rd, and we would have a mismatch. So we have to make sure that these first 90 trading days have no gaps. And that's what makes this code hard. So we're going to run a for loop. We're going to go through all the firms. So we're going to let I range from 1 all the way to the size of the firm cell array in the columns direction, 5194. There's 5,194 firms for which we can compute the abnormal returns. But then within each firm, now we're going to let J run through the rows of each firm's matrix, starting on row 1, and we're going to go row 1 through row 90. We're going to look at those first 90 dates and make sure those are consecutive. Then if they are, we're going to regress these 90 returns on these 90 returns and get those coefficients, those estimated coefficients from equation 1. So we're letting J go from 1 increment by 1 up to the size of that particular firm's matrix in the rows direction minus W. We can't have J go, because we're going, when J equals 1, we're going 1 through 90. We're trying to regress 1 through 90. So we can't let J go all the way to the end, because then it'll try to do this through this plus 90, but it'll say there aren't any more rows. So we have to let J stop 90 rows before this last row. All right. So we want to make sure the condition that has to hold before we will take these first 90 returns and regress those on these first 90 is the following. The first 91 dates, not 90 dates, 91 dates right here have to match the first 91 dates and or have to be consecutive. And so why 91? Well, if we only have the 90 matching, but not the 91st matching, then we can run the regression with the 90, but then to compute the abnormal return on day 91, well, if this date doesn't match, we can't compute that. So how do we find out if these dates right here have no gaps? We already said that these first 91 will have no gaps. Actually, all of these in every row in column 1 of B, there are no gaps in the trading days in the market returns data set. So I'm going to teach you a function here. It's called isMember. And we're looking in the first column of B, and we're going to check. I'll just let I equal 1 for now. We're going to check if for each row of B in column 1, for each row, we're going to check, is that day a member? Can it be found in this column vector of days? Right? So that's what we're looking for right there. Just going to show you, for example, I'm going to call this test. So what does this do? What it does is it goes row by row through B, column 1, the days column, starting with row 1, and it asks, can this day be found in this particular, can that day be found in this particular vector? What is this vector? This is firms 1, 1, rows 1 through 91, column 2. In other words, can we find this date anywhere in here? Well, yes, we can. It's right there. Then it'll ask, can we find this date anywhere in there? And so forth, row by row. And so the output of this, oh, what did I miss? The output of this is a logical vector. What did I type wrong? Oh yeah, I messed up this part right here. Column 2, sorry. The output of this is a column vector of logicals. So on row 1 of B, column 1, we could find that, we could find that in the first 91 rows of column 2 of the firm's matrix. So test on row 1 was given a 1. And then hopefully the first 91 rows of test will have a 1 there, which means that those corresponding rows of B column 1, we could find that those dates in the firm's date vector. But then what we want to do is we want to apply the find function to test. We can either do it this way, find where 1 equals test, or just find test. Those are equivalent here. And what that will do is it will output a double array where it will put the rows of test where there was a 1. So row 1 of test has a 1, row 2 of test has a 1, and so forth. So here's what that will look like. And then we want to apply the diff function to this. So the diff function takes each element t plus 1 minus element t. So this minus this is 1. This minus this is 1. This minus this is 1. So if there's 91 elements, there'll be 90 differences. So that spits out this. And then if we take the sum of this, we should get W. If we don't get W, then that means there's some date. There is some date. That means that there's a missing value here in the firm's date column. So I can prove it. What I'm going to do is I'm going to copy this and I'm going to paste it. I'm just going to create another little vector. I'm going to paste it over here. And then I'm going to go in here in the firm's matrix. I'm going to delete that row. So there is a gap here. And then I'm going to show you if I apply, let's apply the whole thing. So I'm doing sum of diff of find of this. And I'm saying I'll get W if there's no missing date, but I won't get W if there is a missing date. See? There's a missing date. And you can pause the video and go back and work through the logic yourself. And so this is the condition we want. So if, then we can just change this to I, this to J. If this equals W. Then we can compute the abnormal return. We go back, grab little a here, copy that, and paste that back in here. Put that back to what it was supposed to be. I was just showing you by means of example. All right. So then what we're going to do is we're going to set, so if this condition holds, then we can compute the abnormal return. We're going to put the abnormal return in column 5. The abnormal return on day J plus W, column 5, just like I wrote down in the theory earlier, the abnormal return for firm I as of day T plus W. Remember that? W plus T, capital T. Well, the capital T here is like the J. The abnormal return on day J plus W. So the earliest we can compute this is on day 91, because when J starts at 1, W is 90. The earliest we can compute the abnormal return is on day 91. We can't compute the abnormal return on this day because we don't have the previous 90 trading days that we can run that regression and get the coefficients and so forth. But on day 91, for this particular firm, since these dates are all consecutive, there are no gaps, then we can regress the returns in the previous 90 days on the corresponding previous 90 days of factor returns according to our model, get the coefficients, take those coefficients, multiply those coefficients by the actual values of the market factor returns on day 91. That gets us our expected return for day 91, and then take our actual return on day 91 minus our expected return on day 91 should give us our abnormal return on day 91. So we're assigning our abnormal return day 91 when J equals 1, for example, column 5. It's going to be equal to the actual return, which on that day, which is in column 4, minus the expected rate of return. And remember, in our theory, we computed the expected rate of return. We ran the regression, and then we computed the expected rate of return using matrix algebra. We took the 1/5 vector of beta coefficients, beta 0 hat, beta 1 hat, beta 2 hat, beta 3 hat, beta 4 hat, and we multiplied that 1/5 vector by a 5/1 vector of the actual values of the market, the actual realizations on the independent variables, the market factor returns for that same day. But then we had a 1 at the top of that vector. So a 1 and then these values underneath the 1. Remember that? So how do we get the coefficients? We use the regstats function. Regstats, the dependent variable goes in the first argument, and the dependent variable here is firms 1i, rows J through J plus W, but not that. That's 1. If J equals 1, that's 1 through 91. But we want rows 1 through 90, right? So minus 1. Column 4, that's our dependent variable, because we're regressing the first 90 rows of actual returns, rows 1 through 90. We're regressing those. That's our dependent variable. Second argument in the regstats function is our independent variables. So it's a matrix. Column 1 will be x1, column 2 will be x2, and so forth. So our independent variables will be rows 1 through 90 of B, columns 2 through 5. So, but we'll say B, and then to get rows 1 through 90, because it's not necessarily rows 1 through 90. That code won't work generally. Because, for example, if one of these firms' data doesn't start on the first day of our sample, say it starts, on this day, say that's the first day and we have 90 consecutive trading days, well then this isn't going to correspond. These first 90 in this firm's matrix wouldn't correspond to the first 90 in B, right? Because B still has these. So we have to be careful here. We have to say, we have to do the find is member. In other words, this part right here, if we just copy and paste this part, that should work. But here we have to go, oh, this cannot be J plus, say J plus W there to make it general. So this has to be J plus W minus 1. So it's those rows of B, columns 2 through 5. That is our independent variable. The third argument of our regstats function is the model. We're doing a linear regression. And then the fourth argument is which stats do we want? We just want the betas. That's the regstats function. So we're regressing this dependent variable on these independent variables expressed in matrix form. We're getting those corresponding rows of B where the dates here line up with the same dates in B. That's why we did the find is member. And in B, when we run with regstats, you don't have to have a column of ones in B. So in B, we just have our 4 independent variables: the excess market rate of return, the rate of return on the SMB portfolio, the rate of return on the HMO portfolio, the rate of return on the momentum portfolio. We don't have to have a column of ones at the beginning to get the intercept. When you run a regression, you usually have to have a column of ones to get your beta 0, your intercept. But in Matlab, with regstats, your independent variable matrix, this right here, does not have to have a column of ones. Matlab will automatically add a column of ones to it before running the regression so that it can get the intercept when you use regstats. When you use the regress command in Matlab, that function, it's a different function, but it accomplishes the same sort of thing. But with that function, the independent variable matrix has to have a column. You have to put a column of ones in it. Matlab doesn't do it automatically, but with regstats, it does. So let's just see. I want you to see what regstats will output here. Let's just run the first regression. Let me just set I equal to 1, J equal to 1, where we just regress those first 90 rows of the first firm's matrix on the corresponding rows of B. And here is what is output. It's a struct field. It's a 1-by-1 struct array. And inside of that is what we want, the beta coefficients right here, because we specified beta. So inside of that we have beta, and there it's a 5-by-1 vector of the betas. There's beta 0 hat, there's beta 1 hat, beta 2 hat, beta 3 hat, beta 4 hat. This is the intercept. This is the coefficient on the excess market rate of return. coefficient on the SMB portfolio rate of return, coefficient on the HML portfolio rate of return, and coefficient on the momentum portfolio rate of return. But remember, in our matrix algebra, when we were doing that with the theory, we need this to be a 1/5 vector, not a 5/1 vector. And we need to get, when we run this, we need it to output the 1/5 vector of betas. The first thing we have to do is for it to output just beta, we have to say dot beta. Because just this is a struct array with two things in it. We have the source and we have beta. So we want to specify which one. We'll say dot beta, and that will be output. But we want the transpose of that. That's a 5/1. We want the 1/5. So if we took this and just put a if we did this here and just put it like that, then that would be the 1/5. So that's actually what we want. So dot beta transpose. So that's the 1/5. Then we want to multiply that, this 1/5, by a 5/1 vector where we have a 1 in the first row, and in the rows underneath the 1, we're going to have the corresponding values of the independent variables on day 91. Actual excess rate of return, actual SMB portfolio rate of return, actual HML, actual momentum. These actual. But then, of course, we have to take the transpose of that to get that back into a column vector. So we're going to say B. Now all we have to do is do our find is member again, this. But we're not trying to find where this we're not finding those rows of B where this whole vector of dates is in B, but just where one of the dates is just the date on row J plus W. We got that. And then we need to take the transpose of that, because this by itself let's say we let I equal 1, J equal 1, that by itself would just be these four numbers, but we need the transpose. So there we go. End it with a semicolon. And yeah, the abnormal rate of return equals the actual rate of return minus the expected rate of return, all of this, which can be broken up into its two pieces. We got the 1/5 vector of beta coefficients multiplied by the 5/1 vector of actual realized values of the independent variable with the 1 there. So that'll give us the abnormal rate of return according to our theoretical setup earlier. So we need to, all right, before we end the if statement, so if this condition holds, then the abnormal rate of return is given by all of this equation. But what if this condition does not hold? What if this condition does not hold? So then we're going to say else. Then the abnormal return, we can't compute it for that particular trading day. So we'll set it equal to nan. Then we need to end the if, end the for, end the for. So for example, if there was some sort of gap in here in our particular firm matrix. Like right here, suppose this row is missing. So there's a gap in trading dates. We're missing the 11th. Then we would not be able to compute the abnormal return for this firm on day 91. We wouldn't be able to compute this abnormal return on day 91. We have the actual return on day 91, but we can't compute the expected return for day 91 because we don't have, on the 90 previous trading days, there's a gap. The 90 previous trading days, there's a gap, right? There would be a gap. Remember I said if there was a gap in here. And so it would assign that 91st row, column 5. In other words, the abnormal return on May 13th would be assigned nan, because we'd be in this else condition, because this wouldn't be satisfied because there was a gap. So this part of the code is going to take a while to run, but I will fast forward the video and see you on the other side. So we're going to run. Oh, and notice one thing. Nowhere in this code did we tell, we didn't tell what do we want the abnormal return to be on rows 1 through 90. Well, they're not defined, right? Not defined until row 91. So when j equals 1, that's the smallest j can be. So the smallest this can be is 91. So the abnormal return is defined no earlier than row 91. So what so in column 5 on the first 90 rows, what will it put? It's just going to put default 0 because we didn't specify anywhere in here what it would put. It's just going to put 0 all right here, which after we run this code, then we can turn the zeros to nans. All right, so I'm going to run this, and it takes about 30 or 40 minutes, and I'll see you on the other side. All right, our code is finished, and it says here it took 2,295.93 seconds. So we'll just divide that by 60, and it took 38 minutes. So what we'll do here is we'll go ahead and write ourselves a comment and say code takes 30 to 40 minutes to run on a fast computer. Just so we know going forward, whenever we run this particular block of code, we know it's going to take a little while. We can go for a walk and come back and it'll be done. All right, so in column 5 of our firm's matrix, each of our firm's matrices, we should have the abnormal returns. So like I'd said right before I ran that little block of code, I said the first 90 rows is just going to be assigned 0 because we didn't tell, nowhere in here, nowhere in this block did we tell Matlab what to put in column 5, rows 1 through 90 of each firm's matrix. So it just puts 0. Rows 91 through the end, it will either be nan if this condition was not satisfied, which means there's some missing dates for which we can't compute the expected return because we can't run those regressions. Or it'll actually be a number, and these are the abnormal returns, the abnormal rates of return. We have the actual rates of return, and we have the unexpected rates of return, or the abnormal rates of return. Of course, we could get the expected rates of return once we already, in other words, we got this right here from by computing the actual minus the expected. So we saved this and we have this, but we don't have this part, but we could get that back by just subtracting the unexpected from the actual would give the expected if we wanted to get that back, but we don't need the expected. This video is all about, we need the expected so that we can compute the unexpected, but our end result is getting the unexpected rates of return. So now what we're going to do is for each firm matrix, we're going to set the first 90 rows equal to nan. If you can see, the first 90 rows is always 0 here, based on what I just said. So let's, for each firm matrix, so we'll look the size of firms, all columns, each firm matrix, which there are 5,194 of them. We want to set the first W rows equal to nan. Cannot compute abnormal rate of return for first W days in the above block of code indirectly assigns these as 0. So change to nan. Make ourselves some good comments so that we will never be confused when we come back to this workflow. And now all we want to do, go ahead and run this. So those are all nan now. It's first 90 in each firm's matrix. Now we want to combine the firms into one double array again to form the final data set. And the fastest way to do this, we'll call it final data. We just use the vertical concatenate function in vertcat. Firms, cell array, row 1, all matrices. We're just going to vertically concatenate those together. There we go. We'll do that. So there we go. And then we are going to delete all rows which have a nan value in column 5. These are all firm day observations for which we don't have enough data to compute the abnormal return, because we don't have 90 previous trading daily observations for these particular firm days. And so this is what I was talking about earlier. You can see our final data, it's 4,975,969 rows. After we run this, 4,502,886 rows. So there would even be less data left over. So this is all, here's our permno day, SIC4, actual return on that day, abnormal return on that day, using the Fama-French and the Carhart factors, the 4-factor model. And that was the whole point of this video. Now, if we would have set W up here equal to 120 and rerun all this code, we would definitely have less observations left over. Or we would definitely have less observations in our final data. We wouldn't be able to compute the abnormal returns for as many firm days. And that is because of what I said right here. The bigger the estimation window, the fewer firm days for which abnormal returns can be computed. But the reason that's true is because it requires us to have 120 days of prior consecutive trading days of returns to run that regression. And that's a more stringent requirement, less likely to have that, more likely to have gaps and not consecutive days, and therefore you can't run the regression, and therefore you can't compute the abnormal return. So now let's go ahead and convert our double array to a table and put our variable names in it. So we'll use the array to table function. And we will convert our matrix, our double array final data, to a table called final data. And our variables are permno, day, that's permno, that's day, that's SIC 4-digit, that's actual return, that's abnormal return. And if we wanted to get the put the expected return, if we wanted to put the expected return in, we could. Again, abnormal return equals actual return minus expected return. So you put the expected return on the other side. Expected return equals actual return minus the abnormal return. So if we took the actual return minus the abnormal return, we could have a column for the expected return as well in our final data. And I guess I could put that in there. Let's run this. Let's see, maybe I should do it over here. So we'll have final data equals final data, all rows, all columns, or just final data. And then, I'll add another column, and it'll be final data, all rows, column 4 minus column 5. That should be that should give us our expected return. Put back there. Then we can check just to make sure. I mean, actual minus expected equals abnormal and so forth. And then for our matrix, then we need actual return, abnormal return, expected return. Or I guess, you know what I could do? What I could have done. Let's redo this. And then let's put, I want to put the expected between the actual and the abnormal. So final data, be final data, all rows, columns 1 through 4. And then between, in column 5, I'm going to have the expected rate of return, and then in column 6, I will have the abnormal rate of return. There we go. Actual, I put the expected there, there's the abnormal. So in here I'll have now I should say rate of return. These are rates of return. But at this point I'm getting a little sloppy on my, not as precise in my names. So here's our final data set here as a table. Let's run this. And there we go. Permno, day, SIC4, actual return, expected return, abnormal return. I will save this script file, do this, clear the variables, and I hope you guys enjoyed this video, and I will see you on the next one.